Hello everyone, I'm Yaman. I'm a member of Team IMC 4191. Today I'm going to talk about FTC, also known as First Tech Challenge. FTC is an international robotics and engineering program for students aged around 12 to 18. In this competition, students design, build, and program a robot from scratch using real engineering processes. However, in FTC, the main goal is not only to build a robot and compete, but to understand how engineering works in real life. Students learn how to analyze problems, develop solutions, and improve their designs through testing. In FTC, robots are not ready-made systems like Lego. Instead, students use generally metals, plastic, and special connection components to build their own robots. Based on a given theme, each robot consists of four main systems: the structural system, the task mechanisms, electronics, and software. These systems must work together as a whole in FTC. Even a small design decision can directly affect robot's performance. So building an FTC robot requires careful planning and testing. This makes FTC very similar to a real engineering environment. In FTC, students take multiple roles. They are not only building or coding, but also testing and solving problems. A student in FTC can act as a mechanical engineer, a programmer, and a system designer at the same time. Students in FTC also learn teamwork, communication, and project management. FTC helps students understand how different engineering fields come together to create a working system. Each year in FTC, a new team is announced, and the entire season is built around it. In recent years, teams have included Ultimate Gold, Fright Frenzy, Power Play, Center Stage, and Into Deep teams. These teams are not random, they are connected to real-world topics. For example, Into Deep team focuses on oceans and seas. So teams are encouraged to develop projects related to ocean pollution and marine ecosystems and sustainability. The competition field and scoring elements and tasks are also designed accordingly to that theme, making the experience more realistic and more meaningful. FTC matches are lost about 2.5 minutes. The first 15 seconds are autonomous, where the robot runs completely on its own with using pre-written code. After that, drive controlled period begins, where students control the robot using a joystick. Programming is done using Java or block-based coding platforms provided by First. During autonomous mode, teams often use a system like sensors and cameras to make decisions. This process is very similar to real-world robotics and software engineering. A strong FTC robot starts with a solid structure. Most FTC robots are built using aluminum profiles, which forms the skeleton of the robot. These profiles are lightweight but strong. Commonly, types include channel, U-channel, and T-slot systems. These allow flexible designs and easy assembly. A good structural design in FTC ensures durability and stability during matches. The power generated by a motor is not useful unless it's transferred correctly. This is done using gear systems, belts, and chains. These systems help control speed and torque. For example, connecting a small gear to a larger gear increases torque, but reduces speed. Doing it the opposite way increases speed but reduces torque. Belt systems are quieter and more flexible, while chain systems are stronger but require careful alignment. The direction and placement of these systems also affects how the robot moves. Motors in FTC define how the robot behaves. All FTC motors are 12-volt DC motors, but they have different characteristics. Tetrix motors are strong and durable but heavy. Nevis motors are versatile and commonly used in many designs. Matrix motors are compact and modular but not suitable for heavy tasks. Rave HD hex motors are modern, meaningful, and include encoders for precise control. Core hex motors are smaller and used for lightweight and precise mechanisms. Choosing the right motor for the robot is important because using the wrong one can reduce efficiency or cause mechanical problems. The control systems is managed by the control hub, which acts as the brain of the robot. It receives power from the battery and distributes it to all components. Motors, sensors, and servos are all connected to this hub. If more ports are needed, an expansion hub can be added. The control hub also runs the code that controls the robot. Proper wiring is very important because poor connections can cause system failures. Sensors allow the robot to understand and interact with its environment and scoring elements. Distance sensors can measure how far objects are using ultrasonic or optical methods. Color sensors detect different surfaces or game elements. Touch sensors detect physical contact. Magnetic switches detect magnetic fields. The EMU measures orientation, angle, and balance. Potentiometers are used to measure position or angle in certain mechanisms. Using the right sensor correctly is essential for reliable performance, especially in autonomous mode. The chassis is a base of the robot. All systems and mechanisms are built on it. A well-designed chassis provides balance and stability. A tank-style chassis is simple and stable but may have limited movement options. Different chassis designs can be used depending on the strategy and game requirements. Also, there's several kinds of different drivetrains. The drivetrain determines how the robot moves on the field. Tank drive is one of the most common systems, known for its simplicity and control. Mechanicum drive uses special wheels that allow the robot to move in all directions, including sideways. Omni drive is similar but slightly more complex system in control. Choosing the right drivetrain depends on the game strategy and the level of control needed. So thank you for listening. I hope this video provides clear and useful information about FTC.